Greeting people out in YouTube land. This is my first attempt at a serious YouTube presentation on my own. I have been on YouTube multiple times, mostly through the quantum computing group in Washington, D.C. However, this one I want to catch up with some of the work that's been moving pretty quickly about rephrasing special relativity in some new mathematical frameworks. In particular, I'm going to talk about special relativity as an exploration of state machines, which seems to be a very powerful way to go at this. So let's just dive into it. State machine is a concept from computer science in which you have a memory, which is represented below by the brown line with the state 0. And this memory tells you whatever the last state was. You apply a set of rules to that. The rules then convert you to a new state, which you see at the top. Now, even in saying this, the moment I say this about a state machine as a model for the universe is in complete contradiction to the idea that there's an infinite space-time and matter just sort of glides along through it. So please notice this difference because it's important. This is actually saying that you only have one universe. There's no continuum, there's no world line. All of that is just a mathematical framework for how it behaves. So it's a very different way of looking at it in terms of the underlying reality. This says that the matter and energy that we have in the universe, what we think of as now, is the actual state machine. That is what is moving. That is what's changing over time. The behavior of those changes we then abstract and represent as what we call space and time. So this is I can't emphasize enough. This is a very different way of looking at that. Now, the other thing I want you to notice in this picture is that there's a unit. There's an idea that there's a particular increment that you use to move this presentation along, move this concept of the universe to the next stage. So I call this a DAU, and I'll get into that in the next slide. A DAU means a distance activity unit. The phrasing is intentional. Rather than saying length, I say distance because I'm talking about travel. Rather than saying time, I say activity because I'm talking about the ability to change. You know, we think of time as passing by as often as kind of a negative thing. But if we didn't have time, nothing would happen. Nothing would change, nothing would be done, no work would be accomplished. So you really need this concept of activity to make time into a meaningful concept. So the state machine concept is pretty straightforward. Every location, meaning every material point, I'm not talking about empty space, I'm talking about actual material objects, has some kind of an opportunity that its next cycle. They're all given the same DAU. They're all given the same unit, no matter where it is. And then this unit can be used in different ways. And the most straightforward way is the one in the middle. That's where you just use it for activity. So you use the other ones, you do it as a version of travel. You go to an increasingly large distance. Now, I want to give a very informal analogy, but in some ways it's not informal. There's some underlying physical truth to this. If you imagine a car that the accelerator is stuck, you can't do anything with it. It just keeps moving. No matter what you want to do, it just keeps moving. So you say, well, I don't want to move somewhere. What am I supposed to do? How am I supposed to keep from hightailing it out to some destination I don't want? Then you start going in circles. You do what they call donuts informally, and you just keep going around in a circle. And during that time, you can potentially do things like wear a hole in the parking lot if nothing else, but you're essentially curling that activity into a loop, and you wind up in one place. And so that's the analogy for the idea of all the activity goes in a time direction. Then you say, well, actually, I want to move somewhere else. So then you can do increasing levels of a mix of these donuts where you do a loop and just going straight, and you go for a longer and longer distance until you reach a maximum. That would be the far right side or the far left side. So I say this is more than an analogy because these loops correspond to our idea of time. Time always has this circular aspect to it. Your clocks go in circle for a reason because you have to repeat this cycle again and again. So it's an informal analogy, but also it does tell you something about what's going on with this. Another thing to notice about this slide is none of this is what they call mixed signature space. That is, Minkowski introduced this idea that time has to have a negative sign. That just doesn't happen here. There's no need for it. It actually complicates things tremendously. This straightforward relationship between distance and activity actually can be very hard to see if you start changing the sign on time. So this is just an ordinary, what you call a Euclidean space, which just means it just behaves exactly like the space we're used to, but you do have the addition of the time dimension that you go in the vertical direction. So let's break that idea down into a bunch of little bitty vectors, and you have a bunch of little bitty spots. Now, in both cases, you can make these locations as large or small as is appropriate for what you're doing. If you have large units like stars or some kind of anything that has some kind of unity to it that you can identify as an object, or you could go down to the scale of atoms, or you could go down to the scale of particles. It doesn't matter. The idea is that you have some set of entities that you want to then transform under the state machine model. The second thing to notice about this is that the scale of these units can be extremely broad. You can go anywhere from nanoscale, attoscale. If you're dealing with particles, it can be an incredibly small amount. Or if you're dealing with astronomy, you can have incredibly large amounts. You can use light years. So for suns as items, for galaxies as items for that matter, you can have the same kind of application using much larger units of these DAU transformers. Now, the units of these transformers are nominally in time, rest frame time. So like you can say like a 1 hour DAU, that would take you out to about Saturn roughly, when Saturn's close to us. So on the length scale. And in terms of the time scale, an hour is an hour. We know what that is. It's a little surprising to think that an hour is equivalent to a trip to Saturn, but that's what you get from the speed of light. The equivalence, you want to make sure those units match up in that sense. So a year and a light year would be an example of this kind of a square. So this is the framework. This is the starting point. And the assumption is, again, that everybody gets one of these allocations. Everybody gets to use it as they see fit. Now, what happens if some folks want to start hightailing it? They want to stop doing donuts and they want to start heading out to another direction. Well, if you're just one car, then it's just one arrow and you just tilt that one arrow. However, if you want to do a group, like you have a series of cars and several parallel parking lots, you've got to get coordinated. You actually have to organize how it is that you're going to do the start. You want to keep it so that you're all parallel to each other as you're driving. That takes some effort. And this, incidentally, this is, I find this fascinating. This is one of the areas where special relativity and relativity in general has been extremely casual. They just say that acceleration is a second derivative of velocity. That doesn't cut it. There's so much more complexity to the concept of acceleration than that. And we know that from the physical world. So if you focus only on something simple like a second derivative, you're missing the point. You're missing the organization that's needed. You're missing the relationships. You're missing the starting point itself. You can just skip the fact that it takes energy and time to do the start. So all the cars, 4 cars in this case, first they have to get themselves aligned. They have to start out and they're all rev their engines and go out in the same direction, but this time they start acquiring distance. At the same time, they do fewer of the donuts. Remember, the engine doesn't stop. If you're going too fast, say, I've got to do a donut now. And that's your clock cycle. That's where your time comes in. So you just keep moving this way and head on out. And eventually you stay in coordination and you all have a similar view of what you're doing. This is the idea of an inertial frame. And of course, the original starting point was also an inertial frame, a very, very large inertial frame. This is a small one. And I also want to point out that as soon as you do this with a state machine model, you have violated the concept of space as being something separate from the material object. In this case, the only group that shares a definition of space and time are those 4 cars, nobody else, because they had to go through a special effort to get there. If you look at just from the figure itself, you can see they're contrary to everybody else. And they're also a very small fish in a very large pond. So the idea that if you've accelerated, you somehow create this sort of magical space-time that just extends forever, that doesn't cut it. They used to have that concept in physics of, of slicing up the universe based on this perspective. You can't do it if you're respecting this grouping that you have to do. So let's look at the next one. Universe as a state machine is a summary of what I've already been saying. Already saying this thing, but just point this out and emphasize it. The AU model is not a space-time model. There is no concept of space-time fabric. There's no concept of space as a separate existing entity. Certainly no concept of time as a separate existing entity. All of these are simply activities, transformations on a group of objects that have memory, and those objects being matter and energy. So the matter and energy changes on the model, and the way it changes is extremely well organized. And that's why the concepts of time and space are so intrinsic in how we view things. If we didn't have them, we wouldn't be here. But they're in this model, they are behavioral. They're not intrinsic, existing, predefined, anything of that sort. And of course, if you do assume that space and time are pre-existent, you have to explain the complexity of those things because they are very complex. Space-time is not a trivial concept. The idea that it's popping up from these already complex, especially fermionic universe, the matter particles that we think of, actually just makes it a lot easier because you say, well, yeah, I've got fermions, they have complex behaviors, they can coordinate with each other, and all of a sudden these behaviors that we call inertial frames, time, space, come out of that. But time and space in this model are only transformation operators, nothing more. That's a very small view of time and space compared to most models. Now, the same model I just gave can also be simplified in what I call a tilted block model, a tilted block formalism. And what I like about this, I really like this formalism because, first of all, it allows you to get the answers of standard special relativity questions in an almost trivial fashion, which I'll show in a couple more slides. But the other thing is it's just visually intuitive. You can understand what's going on here. You have a block that covers that one increment of time. That's your vector, but it's a collective vector in this case. And you either flop the block over this way, you tilt it over the other way, or you just leave it vertical. So your physical intuition is very good for this. You notice I've got, in this case, I've got it as a long train of some sort. That would be a very long train. So you got this train, and you have an image of it as the state of the DAU state. So again, these are state diagrams. These are telling you how the transformations work. The only physical reality that you have in these figures are DAU 0 and DAU 1. So you have a physical universe is changing state as it goes through. And then these diagrams tell you how to change the state. They're not the reality in itself. The reality, everything in the universe, we can still see that. If something's moving, we still see it in that universe. It's still part of our state. So this gives you the tilted block formalism, and it's quite handy. Oh, the other point I want to make about this is you have to do things to accelerate. I can't emphasize this point enough. Acceleration is not a trivial object, especially a trivial action, especially for large objects. The larger the object, the more difficult acceleration becomes and the more limiting it becomes. This is how you avoid time paradoxes because it's not free. When you tilt these things, you're moving yourself in time and everybody else is moving along also. There's no time paradox. It takes time to construct this. And that prevents you from having some kind of strange idea of going into the past. You don't. You only do what you can. Here are 3 examples of the tilted block relativity, and here's where I want to show the value of this, is that they have an ability to calculate what you would call the Lorentz transformation, and also the Lorentz transformation on length, Lorentz compression, but also they tell you what the times are. And here's a surprise. Einstein said a long time ago that a train that's moving at high speed has different times. It's not simultaneous. this is one of the most impactful statements he made about special relativity, is moving objects are not simultaneous from the view of another observer. Well, this is just a quantification of that same idea, but it's much more specific than just saying it's a relative quantification. It says that, no, you have to attach it. It has to be attached to the original state. And the most convenient way to do that is to make the front end of the object into your 0 point. Then you tilt it in these different ways. You have to actually change the clocks. Also, if these are like satellites, you have to move them closer together. And it takes time to move them close together. Acceleration is not free in any fashion. So you can see visually, you can get a very quick feel. You say, if I move at 86.6% of light, now granted the angle, this angle happens to be 60 degrees in this case. There is an equation that tells you the relationship between this velocity and the angle. But really, if you just think mostly in terms of the angle, you can get a very good idea of what's going to happen. So tilt the block 60 degrees, you wind up getting a speed of 86.6% of light speed. But you also get these marvelous little clock values. And you see that they're delayed. And in this case, the delay is not the same at the beginning and front. Lorentz contraction is simply the projection of these states back onto the reality of the new state. You have to map them into the actual state machine over here, the state memory. And at that point, you get this. These can get wonky. If you look at this one over here in the middle, that one can be, one of the corners can extend up into nominally the future. And it doesn't mean you're going into the future any more than when you shift your hours ahead for daylight savings time or back for end of whichever way it works out. It doesn't mean that you suddenly jumped into the future. It just means you changed how you count for the time. Same thing here. You have to change the time states, but the reality is always the state machine itself. So these things can occasionally here can pop up over in the middle example to where it's above the line and that you actually have to set a time to the future. Once again, acceleration requires effort. Here's a 4S memory tool for remembering that, and also an example using satellites. Why do I use satellites? Because if you use trains, your intuition says, well, I can't squeeze the train closer together. That makes no sense. That only happens after you accelerate and Lorentz compression comes into effect. But if you're talking about satellites, it's a whole different issue. If you're talking about satellites, actual GPS satellites, for instance, this could be a real world problem, then the satellites have to move physically closer to each other. So you pick which ones. You say these are my cars in the parking lot that are doing donuts right now, and say I want to change them. I want to have fewer donuts, and I want to have them closer together. You have to move at one. Usually this satellite it could be different combinations, but you have to move at least one of the satellites so it's closer. And then you have to do this spring forward for your daylight savings time, where you just move the clock forward. But you don't experience this time. This is false time. This is not a real time elapse. You just set the clock forward. And if you were doing this in real satellites, that is literally what you do. You would actually set the time forward and say, well, I'm prepping you for this acceleration phase that's coming up next. And then your final phase is finally where you actually do the acceleration. You push the satellites independently, and then all of a sudden, when you reach the speed that you desired, the clock suddenly makes sense. When the satellites look at each other, they say, do you have the same time I do? They looks back at the other one, they say, yeah, we're in sync again. How'd that happen? Well, because you went through the 4 steps that are required for accelerating an object. Acceleration is not just a second differential. Summary of this: take this universe as a state machine. Boy, does it simplify special relativity. I've only given simple examples here, but all of a sudden, cases where you have multiple frames, objects colliding with each other, colliders of large nuclei even, it makes a difference. You get slightly different predictions for colliding 2 lead nuclei using this model than you do if you try to do it just by assuming each one has its own frame and don't pay attention to the details. This forces you to pay attention to the details of acceleration, the details of collision, the details of the clock time. So everything's Euclidean. It's not that you can't use a negative sigma, it's just that you don't need it. And if you add it too soon, you wind up making more confusion. Where you do use the Minkowski type transformations, it's when you want to see what it looks like from the other person's viewpoint. But that's an explicit step, and you want to be careful about that, because once you do that, you're in that limited, tiny little domain that only involves whatever group did that. And boy, that makes a difference, because it means everything outside of that little domain does not have the properties that you're expecting. Now, one of the coolest things about this is the largest frame becomes a universal coordinate system. And that is not a statement that you would normally see in special relativity. And yet, from an engineering viewpoint, we know that's true. You don't suddenly lose the outside coordinate systems if you suddenly start moving satellites around fast. The time for other groups for the larger set of objects doesn't disappear. It's just that those ones have a new set. Well, what that means is you can always translate back into that full set of coordinates that you originally started with, and then have the other ones as kind of an overlay on top of that. Now, does that diminish the importance of the secondary coordinate system? Yes, it does, and that's a good thing, because if you keep pretending that that secondary coordinate system is something that's applicable to the entire universe, you wind up with violations of speed of light, you wind up with time paradoxes, you wind up with silly stuff that has no correlation to actual measurable reality. So you don't want to do that. You want to have the idea that, yeah, an accelerated object, which you added a lot of energy to, which is not relativistic, that's an event. Adding energy is an event. It also limits the scope of that set of coordinates. Now, inside of that object, you can't tell the difference. That is absolutely still true. So what Einstein said, that was the brilliant insight, that once you're inside that object, you can't do any test that tells you the difference. So predictivity increases with this approach. It is absolutely better for multi-frame tracking, because everything is suddenly in a universal framework where you can say, well, what were the clock times, what were the settings? The universal framework is, now notice, none of this takes curvature into account. I'm not trying to account for curved space in this. So these are approximate within the Euclidean flat space approximation, and they're not trying to do a universal approximation. That'll be an issue for a later time. Again, emphasize space and time as separate entities disappears completely. They're just abstractions of repeated, reliable, predictable transformation operations on the set, on the state machine. Poincare symmetries, you can go with inside its frame, and in fact you have to. You do apply those symmetries as long as you keep them constrained, as long as you recognize the boundaries. If you recognize the boundaries and realize that everything outside of that is something called relativistic Doppler, you're great. If you refuse to acknowledge those boundaries, first of all, you're violating the speed of light, because the universe doesn't care what you did. Your one little spaceship here suddenly accelerated. The rest of the universe doesn't care how you interpret things. Only you care about that. So you have to be careful about the scope of what's going on with that. And those relativistic Doppler symmetries are the ones where if you go to the Andromeda galaxy in a fast spaceship, you will see a blue shift in front of you. And guess what? A blue shift is actually a time shift. Contrary to what many people kind of intuitively think, time does not slow down in the outside universe. It speeds up. It speeds up by a pretty large factor, actually. And time, if you look in the reverse direction, looks slower. The time that counts is always the time that you run into. So by the time you reach the Andromeda galaxy, the blue shift you saw, the faster time you saw playing out as you're driving there, becomes exactly the reality that you get when you got there. The time acceleration is real. You cannot track the universe properly using only the concept of time dilation, because it will not give you an accurate result. And with that, I am wrapping it up. This is my first presentation to talk about an ongoing sequence, fairly fast moving at the moment, of this new approach to special relativity. Thank you.